Hi everyone, I'm Eng Tiong Jia. I'm going to share about Introduction to Deep Learning. Today's session will cover roots of deep learning, second, the root to deep learning, and last one is a success story. Deep learning. Until recently, nearly all of the computer programs that we interacted with every day were coded by a software developer from the first principles. Say that we wanted to write an application to manage an e-commerce platform. After handling around a whiteboard for a few hours to ponder the problem, we would come up with a broad stroke of a working solution that would probably look something like this. User would interact with the application through an interface running in a web browser or mobile application. Second, our application would rely on a commercial database engine to keep track of each user's state and maintain a record of all historical transactions. And third, at the heart of our application, running in parallel across many servers, the business logic, you might say the brain, would map out in methodological details the appropriate action to take in every conceivable circumstance. To build the brain of our application, we have to step through every possible corner case that we anticipate encountering, devising appropriate rules. Each time of a customer click to add an item to their shopping cart, we add an entry to a shopping cart database table associating that user's ID with the requested product ID. While a few developers ever get it completely right the first time, it might be take some test run to work out the kinks. For the most part, we could write a SaaS program from the first principle and confidently launch it before ever seeing a real customer. Our ability to design automated system from first principle that drive functioning product and system, often in novel situation, is remarkable cognitive feat. And when you are able to devise solution that works 100% of the time, you will not be using machine learning. Fortunately, for the growing community of machine learning scientists, many problems in the automation don't bend so easily to a human ingenuity. Imagine hunting around the whiteboard with the smartest mind you know, but this time you are tackling any of the following problems. First, write a program that predicts tomorrow weather given geographic information, satellite image, and a trailing window of the past weather. Second, write a program that takes in a question expressed in free-form text and answer it correctly. Write a program that given an image can identify all the pupils it contains, drawing outline around each. And last, write a program that presents users with the product that they are likely to enjoy but unlikely in the natural course of browsing to encounter. In each of these cases, even elite programmers are incapable of coding up solutions from scratch. The reason for this can vary. Sometimes the program that we are looking for the follow pattern changes over time and we need our program to adapt. In other cases, the relationship, say, between pieces and abstract category may be too complicated, requiring thousands of millions of computations that are beyond our conscious understanding, even if our eyes manage the task effectively. Machine learning is the study of powerful technique that can learn behavior from the experience. As machine learning algorithms accumulate more experience, typically in the form of observational data or interaction with an environment, their performance improve. Contrast this our deterministic e-commerce platform, which perform according to the same business logic no matter how much experience acquired until the developer themselves learn and decide that it's a time to update the software update the software. Although deep learning is a recent invention, have held the desire to analyze data and to predict future outcomes. In fact, much of natural science has roots in this. For instance, the Bernoulli distribution is named after Jacob Bernoulli, and the Gaussian distribution was discovered by Carl Franz Gauss. He is invented, for instance, at least mean square algorithm, which is still used today for a range of problems from insurance calculation to medical diagnostic. The tools give rise to an experimental approach in natural science. For instance, Ohm's law relating current and voltage in a resistor is perfectly described by a linear model. Even Middle-aged mathematics has intuitions for the instance. The geometric book Jacob Collier illustrates averaging the length of 16 adult men fixed to attempt the average. From the figures illustrate how these estimated were 16 adult men were asked to line up in a row when leaving church. Their aggregate length was then divided by the 16 to obtain an estimate for what now amount to 1 root. This algorithm was later improved to deal with mishapen fits. The two men with the shortest and longest fits respectively were sent away, averaging only over the remainder. This is one of the earliest examples of the three means estimate. Statistics really took off with the collection and availability of data. One of its titans, Ronald Fisher, contributed significantly to its theory and also its application in genetics. Many of his algorithms such as linear discriminant analysis and formulae such as feature information matrix are still in frequent use today. Even the Irish dataset he released in 1936 is still used sometimes to illustrate machine learning algorithms. The second influence of machine learning came from information theory, Claude Shannon, and the theory computer via Alan Turing. Turing posed a question: can machine think? In his famous paper, Computing Machine Learning and Intelligence, in what described as a Turing test, a machine can be considered intelligent if it is difficult for human evaluator to test. A machine can be considered intelligent if it is difficult for human evaluator to distinguish between the brain from a machine of a human being through textual interaction. To this day, the development of intelligent machine is changing rapidly and continuously. Another influence can be found in neuroscience and psychology after all humans clearly exhibit intelligent behavior. In thus only reasonable to ask whether one could explain and possibly reverse engineer this insight. One of the oldest algorithms accomplished this formulated by Donald Hebb in this groundbreaking book, The Organization of Behavior. He posited that neurons learn the positive reinforcement. This becomes known as the Hebbian learning rules. It is a prototype of a Rosenberg Bayesian learning algorithm and is laid on the foundation of many short-disk gradient descent algorithms that underpin deep learning today, reinforce desirable behavior and diminish undesirable behavior to obtain good weight in a neural network. Biology inspiration is what neural network is named. For over a century, dating back the model of Alexander Benn 1873 and James Sherrington 1890, researchers have tried to assemble a computational circuit that resembles network of interactive interacting neutron. Over time, the interpretation of biology become more loose, but the new start is hard life. A few key principles that can be found in the most network today. First, the alternation of linear and non-linear processing unit, often referred to as layer. Second, the use of the change rate as known as back propagations for adjusting parameter in the entire network at once. After initial rapidly grow research in neural network language, for around 1993, around 1995 until 2005, this was due to numerous reasons. Training network is computationally very expensive, while RAM was plentiful at the end of the past century. Computational was scarce. Secondary datasets were relatively small. In fact, Fisher-Yaris dataset from 1932 was popular for testing efficacy of algorithm. Minimize is 30,000 handwritten digits for considered huge. Given a strategy of a data computation, strong statistical tools such as kernel method, decision tree, and graphical models prove empirically superior, unlike neural networks that did not require weeks to train and provided predictable results with a strong theoretical guarantee. Next, we're going to talk about the route to a deep learning. One of these changes with the readily availability of large amount of data due to the World Wide Web. The advent of the company serving hundreds of millions users online and a dissemination of cheap, high-quality sensor chip data storage and chip computation, in particular in the form of GPUs originally engineered for computing gaming. Suddenly, algorithms and models that seem computational in fashion become relevant. This is best illustrated in this table. It is quite evident that RAM has not kept pace with the growth in data. At the same time, the increase in computational power has outpaced that of the data available. This means the statistical model needed to become more memory efficient. This typically achieved by adding non-linearity, while simultaneously being able to spend more time on optimizing this parameter due to an increase of compute budget. Consequently, the sweet spot in machine learning and statistics moved from generalized linear models and kernel methods to deep network. It is also one of the reasons why many of the mainstay to deep learning such as multi-layer precision convolutional neural network, long short-term memory, Q-learning were essentially rediscovered in the past decade. After laying dormant for considerable time, the recent progress statistical models application and algorithm has sometimes been linked to the Cambrian explosion, a moment of a rapid progression in the evolution of species. Indeed, the state of the art is not just a mere consequence of available resources applied to decade-old algorithm. Note that the least below barely scratches the surface of the idea that helped researchers archive tremendous progress over the past decade. Novel method capacity control such as drop out allow a training of a relatively large network without danger of overreaching, for example, without the danger merely memorizing large part of the training data. This was achieved by applying noise injection throughout the network, replacing a weight by random variable for training purpose. Come to the last part of the success story of a deep learning. AI has a long history delivering results that would be difficult to accomplish otherwise. For instance, meal is sorted using optical character recognition. This system have been deployed since 90s. It is, after all, the source of the famous and upset of handwritten digit. The same applies to reading a check for bank deposit and scoring creditworthiness of the applicant. Financial transactions are checked for fraud automatically. It forms the backbone of many e-commerce payment systems such as PayPal, Stripe, Alipay, WeChat, Apple, Visa, MasterCard. Computer program for chess has been competitive for decades. Machine learning features recommendation, personalization, and ranking of the internet. In other words, AI and machine learning are pervasive, often hidden from sight. It is only recently that AI have been in the limelight, most due to solutions to problems that were considered intractable previously. Intelligent assistants such as Apple Siri, Amazon Alexa, or Google's Assistant are able to answer a spoken questions with a reasonable degree of accuracy. These include menial tasks such as turning on light switches, a boon to the disabled, up to making a barber appointment and offering a phone support a dialogue. This is likely the most noticeable signs that AI is affecting our life. Again, the above list barely scratches the surface on what considered intelligence and where machine learning has led to impressive progress in the field. For instance, robotics, logistics, computational biology, particles physics, and astronomy all some of their most impressive recent advances and least in the part of machine learning. Machine learning is thus becoming ambiguous tools for engineers and scientists. Frequently, the question of AI apocalypse or the AI singularity has been raised in the non-technical articles on AI. The fear is that somehow machine learning system will become a sentient and decide independently from their programmers and master about the things that directly affect the livelihood of human. To some extent, AI already affect the livelihood of human immediate way. Creditworthiness is mostly navigate car safety, decision about whether to grant brow use statistics as input. More fiercely, we can ask Alexa to switch on the coffee machine and she happily off-flick, provided that the applicant is internet enabled. Fortunately, we are far from a sentient AI system that is ready to enslave its human creator or burn their coffee. Firstly, AI systems are engineered, trained, and deployed in a specific goal-oriented method, while their behavior might give a illustration of general intelligence. It is a combination of rules, heuristics, and statistical models that underlie the design. Second, present tools for general AI simply do not exist that are able to improve themselves, reason about themselves, and that are able to modify, extend, and improve their own architectures while trying to solve general tasks. A much more realistic concern is how AI is being used in our daily life. It is likely that many tasks fulfilled by truck drivers and shop assistants can and were automated. Farm robots will likely reduce the cost of organic farming but they will also automate harvesting operations. This phase of the industrial revolution will have profound consequences on a large swath of society. Truck drivers and shop assistants are some of the most common jobs in many states. Furthermore, statistical models will apply without care can lead racial, gender, or age bias. It is important to ensure that these algorithms used with great care. This is much bigger concern than to worry about the potentially malevolent super intelligence intent on destroying humanity. Thank you for listening for my presentation. For more resources, you can refer to the Dive into Deep Learning.